Okay. Hi, good morning. Thank you very much for this opportunity to talk about our recent work on the application of network control theory in temporal lobe epilepsy. So I'd have to thank all those previous speakers giving the background of temporal lobe epilepsy. Just need to add a little bit here that they are also associated with widespread structure abnormalities across multiple regions in the brain, as well as disrupted neurophysiological dynamics. So, as the structure basis for the brain dynamics, the white matter networks facilitate the energetically demanding transitions between brain states over time. That's how we think, we talk, we work. So during this process, with the development of network control theory, nowadays we can actually simulate the trajectory of specific brain state transition within a linear dynamic model. So as illustrated here, I don't know if you can see the mouse. Yes. So from the transition from an initial state to a target state could take different trajectories. And if we assume the brain is an efficient system as it's supposed to be, then we would expect that the transition would actually take the trajectory minimizing the usage of energy. Therefore, we could have this looking for this mathematical solution to minimize the energy input of the process and identify the optimal energy control energy trajectory of the brain state transition. So once we get back to the epilepsy, we would wondering, will the pathologically altered structure connectivity compromise the brain's ability to efficiently achieve desired brain state transitions? So in order to test this hypothesis, we simulated the dynamic processes of activating specific brain regions and explored whether the control energy profiles could articulate the structure underpinning of the disrupted brain dynamics associated with TLE. In specific, we tested 3 types of brain regions. First, we tested the brain regions under primary seizure influence, such as the ictotemporal lobe in the setting of temporal lobe epilepsy, and we also tested their counterpart, like the contralateral temporal lobe, just as a reference. Second, we tested regions that are less influenced by the seizure, such as occipital lobes. Third, we tested the regions that are not typically seizure origin, but are known to be involved in the seizure propagation and spreading, such as the subcortical areas. Here are some basic information about the group. Note that we only tested left TLE here, and we have demographically matched healthy control data. All their diffusion data were pre-processed with FSL, and deterministic tractography was performed using DSI Studio to generate 1 million streamlines for every subject, yielding individual structure networks with 129 RYS nodes and their pairwise streamline count as weighted ages. Based on these structure networks, we were able to compute the optimal control energy for all regions that are necessary to drive the brain from one initial state to a target state. Let's start the simulation. So our first target will be the temporal lobe. Since we don't know how much a real seizure would activate a target region in comparison to its baseline activity, for simplicity, we set the initial state of every region to 1 in order to represent the average baseline activity. Then we set the target state for the testing temporal lobe to 2, thereby assuming this dynamic process increased its activity by 1 unit. We could test different variations, and I have that by the end of the talk. So then, with all the settings determined, we estimated the regional energy consumption during the activation of the left and right temporal lobe, respectively. Then we summarized those energy consumption globally and then compared between the two groups. We found a significant group by hemisphere interaction where the left TLE patients consumed more energy to activate their pathological left temporal lobe, but not the right temporal lobe in comparison to healthy controls. This result cannot be replicated if we randomly rewire their structure network before the energy estimation, indicating that this result depends upon the topological organization of their structure network. Locally, this interaction was mainly driven by the extra energy consumption at left middle temporal lobe and left hippocampus in those patients. In our second simulation, as I explained, we estimated the regional energy consumption during the activation of left and right occipital lobe, the regions that are less influenced by the seizure. Once we summarized the energy consumption globally again, this time we could not find any significant group differences, either using the real network or obviously using the non-network. So in our third simulation, we estimated the regional energy consumption during the activation of the left and right subcortical areas in the same setting. This time, instead of an interaction, we actually found a main effect of the group, whereas the left TLE patients actually needed extra energy in both hemispheres. This is actually quite in line with the observation of bilateral involvement of these subcortical areas during the seizure propagation and spreading. As expected, once we randomly rewired their structure network, these main effects diminished immediately. Lastly, we simulated a scenario mimicking seizure spreading from the temporal lobe to the subcortical areas. Here, we find this interaction back again, where the left TLE patients consumed more energy during the left-sided spread, but not the right-sided spread in comparison to healthy controls. Locally, this interaction was driven by the extra energy consumption in the left middle temporal lobe, left hippocampus, as well as left putamen. Interestingly, the energy consumption at the left hippocampus was negatively correlated with the age at epilepsy onset, suggesting that this influence might have some developmental relevance. So in summary, we simplified simulations of brain dynamics during seizure onset of spread. We showed that the control energy profiles can specifically articulate the pathologies in temporal lobe epilepsy patients. This observation may be related to the adverse effect associated with the seizure reoccurrence that might compromise the integrity of the structure connections underneath those regions, thus making their activation more difficult. I'd like to thank my mentors and my colleagues for their help with this project, and I'd also like to thank AES and NINDS for their funding support. Thank you all for your attention.